we're going to use this as a means of leaping forward to understand fully what's going on with this uniform circular motion, as well as making a tie to gravitation. And then we're going to make a bigger tie later into really how gravitation works. So what I'm going to ask that you do is let's get something to write with right on. I'm going to ask you to get something to write with and write on. Ideally, you have a physics notebook, so let's take out a physics notebook. I'll give you guys one moment to go ahead and get that. So hopefully you got your notebook, something to write with, write on. What I'm going to do is I'm going to draw what it would look like if we're standing on the ground and you're looking up at that fan, seeing the cat move on this fan, and observing the cat move on the fan. If I do this little dash line right here, we know that that R is the radius, and we can see by looking up at the fan, the cat is rotating around. We'll go in the clockwise formation. So this cat is rotating around on this fan. And what we're going to observe is this UCM. For UCM, this is talking about uniform. And a uniform, that's something that's constant. It's something that's the same. Uniform, circular motion. So we're talking about an object that's moving constantly in a circle about this center point here. So we saw that cat undergoing this uniform circular motion. And what we can do now is we're going to look at this cat's motion, and we're going to talk about some vectors. So there's going to be some vectors that we're going to be interested in. And we're going to describe these vectors, and what a vector is going to tell us is it's going to tell us two different things at the same time. It's going to tell us how much and which way. So a vector tells us how much and which way. So when we talk about a vector, it's going to give us a direction. So that's going to be that plus or minus. That's often the times when we talk about which way, plus or minus, when we're talking in one dimension, and how much, that's going to be the number. So we're going to talk about how much and which way for these vectors. So this vector that we're going to be interested in at first is I'm going to relate back to force. So there's going to be a force as a vector, so we can have 100 newtons in the positive direction and 100 newtons in the negative direction. We're also going to be dealing with a vector for an acceleration. And then lastly, a vector for the velocity. So this cat, when it was on this fan, it always had a force going towards the center. It was connected to the string. So that string that was connected to that fan, that's what the cat was holding on to. So it then will have this force going towards the center. And it does it at all points where there's going to be this force going towards the center at all points around this circle. So this force is going towards the center. So we see it when it was connected to the string of the fan, the string on the fan, which was towards the center of the fan with respect to the cat. This force was towards the center. It's towards the center of the circle. Now we know something about force and its relationship to acceleration. We know that this net force equals mass times acceleration. Mass is just a scalar. In other words, you can't have a direction for your mass, but you can have a big amount of mass. So this acceleration, which is equivalent to the net force in terms of the vector, so this vector then for the acceleration is going to be in the same direction of that net force. It's going to be towards the center of the circle. So this force going towards the center, force is going towards the center. So that means this acceleration at all points is also radially inwards towards the center of the circle. So while this force is radially inwards towards the center of this circle, we're also going to have this velocity. The velocity is different. It's going to form this 90-degree angle with respect to the force. So this velocity, which forms this 90-degree angle with respect to the force, is now in a different direction than the force itself. So the force is going towards the center of the circle. The velocity is not towards the center. So we're going to see that this velocity has a constant speed. Hence the term uniform circular motion. So this is going to be a constant speed. So we're going to be dealing with uniform motion, so it's constant, but it's changing its direction. So that tells us that if it's a constant speed, but it's changing its direction, that means the velocity is going to change as well. So there's a change in the velocity. And this 3 dots right here, this is the mathematical therefore. I'm just using the therefore. The velocity is constant because we're keeping a constant net force radially inwards. So it's not that it's constant because the force is 90 degrees with respect to the velocity. It's constant because we have a constant net force. So this force that's going towards the center is constant, constant, constant. Without this force being constantly towards the center, then this velocity would not be a constant speed. It would vary depending on the force that's being applied towards the center. But that's a good question as well. But this velocity has a change in direction, hence a change in the velocity. We're also going to see that it's forming a 90-degree angle with respect to the force. So this velocity forms a 90-degree angle with respect to the force. The velocity is also tangential to the circular path. So this velocity forms this 90-degree angle with respect to the force, and that's also a nice way of saying that it's tangential to the circular path. So this velocity being tangential, if we were to draw this entire vector line, only one point of that vector would actually come in contact with that circular path. And that one point allows it to be tangential. So now we have the direction of this velocity, we have the direction of the force. We can also now quantify. So we have the which way, but we can also get how much. So this force went towards the center. It's known as centripetal force. I'm just going to call it F sub C. When I mean F sub C, it's this centripetal force. I like to think of it as a force that goes in a circle, but I'm going to write over here it's fictitious. It's fake. And I don't mean, fake like your friends that don't call you on your birthday. I don't mean fake like your, I don't know. I mean fake as in a centripetal force can be quantified by this equation, this M V squared over R. It can be quantified with this, but there's no centripetal anything that caused this cat to go in a circle. So the cat went in a circle around the fan because it had its claw stuck on the string. So this centripetal force that the cat felt was force due to tension from the string. So this centripetal force is fake because it's not real. There's no centripetal object that will make the force move in a circle, but rather for the cat, it had to be the string making it move in a circle. That string was this force due to tension. But we can quantify how much that tension need to be based on the mass of the cat, how fast the cat is moving, and the radius that that cat was operating in that circle. So this centripetal force, while it is fake, it's fictitious because it's really the tension that was causing it to go in a circle. So we're going to take that and we're going to look at the same type of scenario where we have this circular path and I'm going to put in the center of this circular path an object that I could call the sun. And I can place an object outside of the sun like the earth. We know this earth feels this force due to gravity towards the sun. We also know the sun is going to feel the same exact force due to gravity. It's a Newton pair. So we can make these, mark those as equivalent. So in order to have the force due to gravity on one object, there has to be a force due to gravity equal and opposite on another object. Newton's third law. So the mass of the Earth is so much smaller than the mass of the sun. The sun is so big in comparison to the Earth. So when we talk about an orbit, we talk about the orbit of the Earth about the sun. And so what we're going to do today is we're going to say that this sun is kind of fixed at this one point. It's fixed here in the center. We do know that the sun will also orbit as well about the Earth, in a sense that it will move a little bit. The sun will move a little bit. It will oscillate in its position due to the relative position of the Earth and the sun. That's because it will feel a force. If it feels a force, then there's going to be a change in its motion. We're going to assume, though, for today, that this force does not exist. Therefore, we can keep the circular path around the sun. We can say that it's an exact circle. Next week, we're going to make a jump forward. We are going to include its Newton pair, the force due to gravity. And by including that Newton pair, then we're going to see the Kepler's laws of planetary motion, where we see that this Earth does not go around the sun in a circle. It actually forms this ellipse. But we're going to assume a circular path today because we're saying that this sun is fixed in its position. If this were true, and it is, where this force due to gravity is felt by the sun, pulled towards the Earth, what we would see is the two objects rotating about one another. So we would see the two masses orbit one another. So we would see both the sun and the Earth rotating about one another. That would be a binary system. Binary because there's two, 1, 2. I like to think of it as my daughter going to the park. My daughter's 2 years old, and I took her to the park over Veterans Day, and so she grabbed the hands of another kid, and they were spinning around in a circle. They're about the same mass, so both of them were spinning about the center, right about here. They were spinning about that one point, and both were spinning about that. Then my daughter wanted me to pick her up and spin her as well. So then I, at the fixed point of the sun, a lot more mass than my daughter, here the Earth, I was able to spin her around and keep myself fixed in that one point. So I like to think of it like that because the sun has way more mass. Now, it could be this for the sun and the Earth. I could also say, well, this could be for the sun and Venus. This could be for the sun and Saturn. This could be for the sun and Jupiter. It could also be for anything, a larger star. It can be for Betelgeuse and the planets orbiting Betelgeuse. It could be for Alpha Centauri 5 and the Class M planet around Alpha Centauri 5. It could also be that this would be Earth. And this could be the moon. Or with this being Earth, we could also call this a space station. Where this space station is going to feel this force due to gravity towards Earth. Same thing, the Earth, space station, same thing just like the sun and the Earth, all having the same thing to where it's not just one object that feels this, but every object feels it universally. So this is why we call it the universal law of gravitation. So this universal law of gravitation can be quantified with this capital G, m1, m2 on r squared. So this capital G, this is a constant. This isn't like the lowercase g. This is a very small force, or small constant here. So this is 6.67 times 10 to the negative 11 Newton, I think meters squared per kilogram squared. So this is a number with 10 zeros and then finally a 6. So we see that this is really small. So what we're seeing is that gravity is attractive. Gravity will always pull things together if they have mass. So if an object has mass, that means this is going to be an attractive force. This gravity is going to pull together this space station towards the Earth. So this is going to lead us to a thought experiment. So Newton was a brilliant guy. He invented calculus. He also had a thought experiment that can now be known as Newton's cannon. So in Newton's cannon, we're going to look at the Earth, and on top of the Earth, I have a really tall mountain. And on top of that mountain, I have a really powerful cannon. And I can take this cannon and I can shoot a cannonball. And when I shoot a cannonball, it's gonna fall down to the Earth. I can do my next shot with my cannon and I can shoot it faster. If it goes faster, it goes farther, but still falls down to the Earth. I can do my next shot and I can do it even faster. So if I go even faster now, then this next cannonball also falls, still falling, and it falls the entire time. But as it's falling, it keeps moving, and it went fast enough that it's now in orbit. So we see that it's now in orbit. Because it's falling. So the first two, this one had a fast velocity, but it fell down to the ground. This next one had a faster velocity, but it still fell down and hit the Earth. This next one had a faster velocity, and it fell down too. All these objects fell down. It's just this one had a fast enough velocity that it was able to fall and miss the Earth. So it went into orbit because it was falling towards the Earth. Now, if we had no gravity, this object would go in a straight path. If there was no gravity, this object would be shot from this cannon and it would just go in a straight path, which is going to take me to back to our cat. So when we talk about this cat, we saw the cat hit the wall. When the cat hit the wall, it had to let go of the string. So I'm asking you all now in the chat, at what point did the cat have to let go of that string in order to hit that wall? Is it point A, point B, point C, or point D? At what point did the cat let go to hit the wall? All right, so I'm seeing a mixture of responses here. So some of us are saying point B, some of us are saying point A, some of us are saying point D. So if we let go at point B, if there was no more force at point B, then this cat would be following along here and he would have gone off and landed on his cat carrier. He'd be fine. If the cat let go at point A, then this cat would have gone over here and landed on the couch. If we let go at point D, this is where the interesting fun part came in. Because when we let go at this point D, that's where this cat went and hit this wall because it went in a straight path with no more force applied to the cat. The cat went in a straight path and hit the wall. With no more force acting towards the center of a circle, the cat no longer went in a circular path. It went in a straight path because now the forces on it were balanced. With the forces being balanced, the cat had this straight path hitting the wall, taking us back over to Newton's cannon. If there's no gravity, I could take this pencil in my hand and I could throw it and it would go in a straight path and it would leave Earth. But we know there's gravity because stuff goes down and hits the Earth. So we know that there is gravity. And so this takes me back to the reason why I am no longer allowed to watch space movies with my wife. My wife, she said I'm not allowed to watch any space movies with her because sometimes in the movie they'll say, hey, there's no gravity up on this space station. And they'll say, look, we got this pen, it's floating in the air, it's just floating there. Whoa, it's crazy. And with it just floating, and they can't even get some water just floating. Well, what they're saying is wrong. There is gravity. If there's no gravity, the space station falls down, hits the Earth. Or if there is no gravity, then this object is not in orbit. If there is no gravity, then that space station leaves Earth's orbit. If there's no gravity, they're saying they don't have mass. So what they're saying when they don't feel gravity is really they don't feel the opposition to the force of gravity. So I like to think of gravity as sort of being on an elevator. So right now we feel gravity because we have an opposition to it. We're sitting on a chair. We're sitting in our bed, on the floor. Whatever it is, we're sitting on something and something's pushing up. So we have this gravitational force down and we have an opposing force up. So if I am in an elevator and that elevator cord gets cut, I no longer have that opposing force up. I only have that gravitational force down. So that gravitational force then is going down, just like in the space station, without that opposing force up. So in the elevator, it would appear as though my pencil here would be floating. It would appear that my cup of water would be floating in the air because the floor underneath me is falling with me. So I wouldn't have anything to fall to because everything is falling with me. So on the space station, they do feel gravity. In space, they do feel gravity. That's why they're able to stay in orbit. They have mass, and they're in orbit around the Earth. So we know they have gravity. They feel it. They just don't feel the opposition to it. So just like the elevator, while you're falling in the air, that doesn't hurt while you're falling. It's when you hit the ground. That's the crappy part for falling in an elevator. It's that ground, that opposing force of gravity. So whenever they say that in movies or TV shows, I hope you yell at the TV too, and I hope you yell at the movie too. So that way whoever's with you gets very annoyed and they miss the entire plot of the movie. So what I'm going to ask that we do now that we have some notes, what I'm going to ask us to do is let's open up our physics packets.